Hi everybody, welcome back to day 2 of our R lessons. Today we are going to deal with one of these fundamental issues that one just has to be able to do, which is to get data into R from external files. So we'll be looking at a couple examples of how to do that. Thanks again to Diplomix for putatively funding the series of lectures. You should have access now to a script for day 2. R programming B. It was in a directory that either appears in the description of this video on YouTube or that is available to you already from the shared files for this class. We are going to start by simulating some data. This gives us the ability to then write that table to disk. We'll try to cover some of the advanced operations we're going to do along the way. Hopefully most of this will make sense. Remember, of course, that anything with a hash symbol in front of it is a comment. So we're going to start by creating a vector of names. I come over here to R, and I'm just going to enter that line right there. Now you can see that I've given the software a whole series of names. I wasn't actually familiar with all of these, but these are apparently pretty popular names across South Africa, so that would be a fun example rather than looking at Betty and Alice and Charlie to break out the Bongani and the Lindelwa and the Temba and so on. So we have created a vector of these names by the create function. That's right there, the compose function. That's creating a vector, and then we pass that to another function called sort. So even though we passed the software Bongani, Lindelwa, Temba, Dumisa, etc., we should take a look at what resulted in names. We see that what happened? Oh, I'm sorry, I kicked my the button there. I think that it's not showing me the full screen here. Oop, goodness me. I'm just clicking everywhere. Okay. Right, so we passed it the names Bongani, Lindelwa, Temba, Dumisa, Tandiwe, etc. And yet we see that Bongani remains at the start position, but now Dumisa has moved up 2 in the ordering. So I would note that although we think of sorting numbers primarily, R does know how to sort strings as well. It can do an alphabetical sort there. So here it has given us a nice sorted vector of names to begin with, and we've stored that in just an ordinary old variable of vector names. Now we needed to have some averages to work with, and so I've decided to do a random sampling of these. That means that when you run this on your computer, you're going to come up with different numbers than I do on mine. So I'm going to copy that in to run the next line. And I see averages, looks like that. So I note that these are normally distributed. That's why we use the rnorm function rather than runif, for example. We specified that we wanted to get 7 numbers out, and those correspond to the 7 names that we produced. They have a mean value of 0.8 and a standard deviation of 0.1. So do these values look like they correspond to 0.8 mean? As I see, I've got a high value of 0.92. That's pretty high by comparison. I mean, that's more than a standard deviation away from the mean, but that happens. Great, so we've created a vector of names now and a vector of averages that we're going to use as our mock-up data. Okay, now I want to store these in a matrix, so I'm going to use the quiz scores object to hold all of that. We can see that matrix is the outer function on this, so matrix is going to give us, is a constructor function. Whatever you feed to it becomes a matrix. We're going to give it a whole bunch of not applicable values. We're going to specify that it has 7 rows and 10 columns, and that we're going to have names associated with it. And those names are the names of the vector of names that we had here, so that those are not going to go into the matrix, but rather be labels for the matrix. And we're also going to have a series of quiz scores that we give for each one. That's Q1 through Q10 here. So if we simply look at the value of quiz scores after running that, you should see an empty matrix, basically. The vector of names that we provided shows up right here in alphabetical order as we specified, and then the quiz scores appear across here. But at present, quiz scores hasn't been populated with actual values. Okay. So now for each student, we want to simulate quiz scores. And for this, we're going to use a loop. Now, we're going to talk a little bit more about program control at a later point, but for now, I'm going to just copy this block right here. Everything down to the second curly brace. You see that? So here's curly brace 1, here's curly brace 2. We need all of that at once. Okay, so I want to try walking through what's happening here. Remember that we used the series operator yesterday. So if I say 1 to 7, that's equivalent to all of the numbers from 1 to 7 inclusive. Now, you see that I've used a for statement, and I've stated that student should be somewhere in 1 to 7. What that means is that the software is going to iterate. Iterate is something that happens a lot in computer programs, that we're going to repeat the same block of code multiple times. The first time that it does this quiz scores line beneath it, student is going to be equal to 1. The second passage through, student is going to be equal to 2. The third time through, student is going to be equal to 3, and it's going to keep going until student is equal to 7. So this is just a handy way to process up a bunch of results where you're changing what that value is equal to. I want to note that this has already had a big impact on quiz scores. If I play that value back, you see that all those not applicables have been changed to numbers. Now my numbers are going to be different than yours because these are just random numbers basically. Before, we talked about using things like RUNIF for generating randomly distributed numbers from the uniform distribution. We've used rnorm for generating numbers from the normal distribution, but now we're using one called the Poisson distribution. And the reason for this is that when I give exam papers, I hate score results that are like 17.5, right? I wanted these to be integers. And the Poisson distribution is really easy for us to get rounded numbers like that. Okay, so I've asked the Poisson distribution then for 10 values, but I've done something a little odd here, and I want to try to explain that. The Poisson distribution doesn't really have a mean per se, so much as it has a lambda value, and the lambda value is kind of like the typical result for this. You'll remember up top, we created this vector of numbers called averages, and your numbers will be different from mine because you're running this on your computer, but what we were doing was creating randomly an overall appraisal of how the students do. So so student number 1 was going to have an average of about 71%. Student number 2 was going to have an average of about 86%, 93%, 78%, and so on. So these Poisson numbers that have been modeled here, these dummy quiz scores correspond to what those expected averages were for those students. Okay, so far, we've made up a bunch of numbers, and it might seem like that's a really weird way to start, but I wanted to have a data model here that was complex enough that it was worth writing to the disk. In this case, quiz scores represents a score sheet from 7 students who were in a class through 10 quizzes. And so now we have those data put together. All right. Having created the data, it would be nice to be able to write that to disk. Maybe I want to use it in R later, or maybe I want to pass that data off to a spreadsheet. So I'm going to use the write.table function to do that. Write.table accepts as its argument what variable contains all the information you want to write out, which is our quiz scores number variable. It requires that you specify a file name. Here I'm giving it quizscores.tsv, and now I've got a sep in here. I'm setting sep equal to \t. Now, if you're a computer programmer, that's all completely sensible. You probably recognize all these things, but computer programmers are weird people, so let's try to walk through it a little more carefully than that. All right. So I start by naming this file TSV. Now, I'm going to be writing a text file to the hard drive. So why would I call it TSV? Someone's seen this. Okay, so yeah, a TSV is a tab-separated values file. Tab-separated values. Frequently, when we write tables of information to disk, we use the tab character, right above caps lock on your keyboard, to indicate where the next column starts. Sometimes we use comma-separated values files, CSVs. And in that case, instead of using a tab, you use a comma. However, those tend to be a little harder for people to read, so I very frequently use tab-separated values. This sep business reinforces that. So we are going to separate the columns from each other by tab characters. But see, if I just use a tab key in here, boom, like that, it creates a bunch of spaces in here. It's not a correct way to represent a tab. So we use \T to inform R that we wanted to use tab characters. You could use something like \N and it would actually create a new line after each thing, but that's not what we want. So let me actually run that bit of code right there. Okay, so now it has created quizscores.tsv. But where did we just create a file? Does anyone know? If you're doing this in RStudio and you've created a project for this particular class, it'll be in that directory. In this case, though, it's written in the current working directory, which on a Windows machine is typically my documents, I think. So there's a bit of shorthand here. You can take a quick sniff around to see where you are with list.files. Oh my goodness, I've got a bunch of junk in here. Look at all that. Okay. Well, yes, I recognize where we are. We are in my current. We are in my documents folder. So one way to find out is to click on the Change Directory option from the File menu, and you can see that it's highlighting this PC, My Documents. Great. So can I actually do anything with that? Let's go to that directory. On Explorer, I can just come over here. I've got them sorted by date modified, and I have quiz scores right here. I'm going to open Excel. You don't have to do this on your computer if you don't want to. I'm going to just open up Excel now, open a blank workbook, and close that sheet. Now I'm going to just drag, oh goodness, I'm going to drag quiz scores TSV over to Excel. Okay, happily, Excel knows exactly what to do with TSV files. But I see that each of our 7 names is represented in the column, and we have quiz scores here. But do you notice something odd that's happened with this sheet? Yeah, the column labels in the top row all get shifted one to the left. This is kind of an odd tendency for this tab-separated files import. So generally speaking, if you create a comma-separated values file or a tab-separated values file, Excel will just open it, and other than that little problem with the top row, everything is very easy to work with. So getting data out of R is pretty easy for that. We'll look at examples of how to read data from Excel files at the end of today. I'm going to go ahead and close this down. All right, so I can now return to R. Having written this table to disk, I would like to know a quick reminder of what kind of object I started with when I wrote that file. Do you remember we used the matrix constructor function to build this table in the first place? So true enough, the object that we wrote to the disk was called matrix. All very straightforward there. However, so yes, try to import this table into Excel. Note that the header row is shifted. I left myself a handy note. That's good. All right. So this time, we're going to try reading that file that we just wrote. So read.table is the corresponding function to write.table. Nothing too mysterious there. Again, we provide the file parameter to know which file we're going to read. We need to specify what kind of separation was used. The software doesn't just automatically know that a TSV file was tab separated. And we need to specify that that file had a header. Remember, quiz 1, quiz 2, quiz 3, those are all part of the header line. If we don't tell R that it has a header, it's not going to assume it for us. All right. So now when I look at this object that we've created from reading that table, something's happened. Did you notice that? So we wrote an object that was a matrix to the hard drive. When we read it back from the disk, R assumed that what we wanted to create was a data frame. So quizzes and quiz scores are different. Quiz scores is the object we wrote to disk. Quizzes is what we got back from reading it. All right, what else do I want to say about this? Okay, so I can ask which quiz gave the students the most trouble. So I'm going to use the summary on quizzes to get that information out. So quizzes is now a data frame. It sees each of these vectors as having a different name to it, Q1, Q2, Q3. At a glance, it's pretty easy for us to tell if any of these quizzes have a mean that's substantially different than the others. The first quiz was 3586, second quiz was 2943, 30.71, 31, blah, 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 blah. We can sort them, in fact, by those means if we wanted. So these are some of the summary is kind of our most basic tool for data summary, really, for data exploration. All right. We now want to compute an average for each student. You see this row means function? Remember that the rows in quizzes, if we just play back the value of quizzes, each row in quizzes is going to represent a different student. So if we want to compute the mean for each row of the matrix, or of the data frame in this case, we can use the row means function to get at that. Quiz averages. And so very, very rapidly we can pull out the information about how each student did on average. Great. Oh, with the averages that we compute at the start. Yes, that's correct. It has to do with how a lambda, remember that the averages that we set up at the beginning do not directly determine what scores they got. It's used as a lambda value for the Poisson sampling, but the Poisson distribution is not necessarily the same values as what we fed in. It's giving us random numbers based on an input lambda value. So the averages should be in tune with that. A student with a high value here should have a high value here as well, but with some limitations. Let me take just a moment with rows and columns in this matrix, if we could. I'm going to return to the variable that we wrote up top here. So the file that we wrote was based on quiz scores. I want to work with that for a minute. So quiz scores. All right. I want to point out that the software gives us the ability to do indexing much as we did before. Remember that we had vectors of numbers and we could pull out the second item or the fourth item, stuff like that? You can also do that with a matrix, but the syntax is a little different. Let me try to walk you through these two lines. When you try to index out a row or a column from a matrix, you need to specify whether you're trying to get a row or a column out. I'm gonna do one other example here. So if I say quiz scores 1, 1, that means give me from the first row in the first column what value appears there, the 28. See that? If I ask the software to give me the first row, I would say that by saying 1, comma. You note that I've left out the second number here. So I'm specifying no column and R assumes I mean all of them if I leave it out. So quiz scores 1 comma is going to feed back Bongani's whole vector. Remember that the vector is basically a one-dimensional matrix in this case. If I leave out the first number, but I include the second number, the software assumes that what I want is the first column rather than the first row. Yeah. So some of that is going to show up as we move along, but I didn't want people to get completely lost with that. Giving the first value gives you a row. Giving the second value to a matrix gives you that column. If you supply both a row and a column, you get just that information out. And you can also do some fairly bizarre things, like specify a column range. Sorry, a row range. I put it in the first position. So here I've specified that I want rows 1 through 4 inclusive. I could also specify a series of these. Here it's grabbing the first and the fourth, but not rows 2 and 3. So it's possible to use indexing as a way to subset these matrices and grab out just the row that we care about. All right. So which quiz gave them the most trouble? Oh, okay. So sometimes, let's return now to the version of this that we read back from the disk. Remember, it's a data frame. It's a data frame rather than a matrix. We found that out up here with the class command, or the class function. So we want to add, we just computed the quiz averages by using the row means function. What if we were going to print this as our grade sheet for the class? It would be really handy for the class average to be on there. So let's try sticking it on there. We're going to use the column bind function to stick on that row to the bottom. So quizzes plus average is going to have another column bound onto it at the end. So quizzes plus averages now looks like this. And see that it remembered that the variable we stuck onto the end had the name quiz averages, so it just uses that as the name for that column as well. All very handy. Yeah, so. Right. We remembered that Bongani was the first student in this roster, so we're going to use our index function to grab out the first row. That's 1 comma. All right. So Bongani row still bears the name Bongani at the head, and it's got all of these different column headers that are all very much in place. Okay. But it might be that I want to see what was Bongani's highest performance and what was Bongani's lowest performance. So if I use sort Bongani row, then I'm going to see that the worst performance for Bongani was number 17, and the best was a score of 31. So in some classes, if you have a very, very generous teacher, the professor says, okay, we're going to throw out the bottom 2 scores for every student. And then if you have a good first 8 quizzes, you can really slack off the last 2. So yeah, this is the kind of way that you can get at that information very, very quickly. All right. So that was just a simple matrix. This time, I want to work with a data frame instead, because a data frame most frequently represents the kind of information that we work with in biology. So I'm going to copy all of these lines, everything but the write table for now. All right, so we're creating a vector of sexes, female, male, male, female, 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 male. We have a bunch of height values, a bunch of weight values. These are pulled from the normal distribution. Maybe some systolic blood pressures, some diastolic blood pressures, and we created a data frame from it using the data frame constructor, feeding it names, sex, height, weight, diastolic, systolic, and diastolic. Okay. So when we play back the current value of vitals, we see that we have 7 people, and they have the same names of our students. I just use that same vector all over again. I hope you don't mind. I don't think that constitutes a HIPAA violation of any sort. So
the system recognizes those are female and those are male.
in this case, I made it up.
Made it.
Yeah, so you remember that we created the variable sex up here? Female and male, male and female. I hope I got the associations mostly right there. Is Bongani always a dude? Because that would be embarrassing. Okay.
Bongani is a boy.
Bongani's a boy. Oh, that's just embarrassing. I'm so sorry. I'm sorry. That was my mistake. That was a typo from me. Am I forgiven or?
I was thinking maybe the system can be able to recognize.
Okay. No, the software does not know that Bongani is a guy's name. Sorry. I know a guy who's a Bongani. Have I met a woman who's a Bongani? I'm not sure. Okay. Well, I'm sorry about that. Anyway, we have our table of vital statistics. Great. So if we run class on vitals, it notes that that's a data frame, not a matrix. But glancing at it, you know it's not a matrix. Why? A matrix always contains the same type of value in every row and every column. Every row and every column is going to be the same type of value. In this case, we have names that are a column of character strings, and we have sex, which is in here as, I think, a factor. So class vitals $sex lets us examine just that one column. So that one column is coded as a factor. It knows that there are only 2 kinds of values that can appear there. Class of vitals $names shows that it's also a factor. Now, is that what we want? Not really. Not really. I mean, what if we had 2 students named Bongani and suddenly they're coded as the same person? That would be weird. Okay, so sometimes data framing something can make things into factors that shouldn't be. Okay, we are now going to write that table off to the disk. Again, as a tab-separated values file. All right, so if I do list.files vitals.tsv, oh, what did I botch? I don't know that you can specify that. It's in there somewhere. So yeah, there's vitals tsv right there. Great. So now we're going to run a summary on vitals. Okay, so we see that there's already a weird effect popping out of names being coded as a factor. It notes that Bongani appears once in names, Dumisa appears once in names, Kwesi appears once in names. Sex is okay, right? We wanted to recognize that the girls are, that the women are all women and that the men are all men, etc. That we have heights, that the height is recognized as a numeric. Therefore, it gives us this 5-point summary plus the mean. Weight is a numeric, systolic is a numeric, diastolic also a numeric. Okay. So we want to save this in another way as well. Sometimes you don't want to write as a table because you're exporting to Excel, for example. Maybe it's valuable for you to write this particular object to the disk in a way that only R can read, because you're writing it as a data frame in just this format and you're going to read it as a data frame at a later point. So for that, we can use the save function. Before we used write.table for this, now we're saving it. It doesn't matter what kind of object it is in R. If you specify to save that object, you can give it a name and specify that it's an R data type of object. You can then reload the object at a later point in time. Now, what's missing from the load that we had in the save? Both of these are taking the file argument. This is equivalent to saying load files, a file equals vitals R data. But it doesn't specify that the variable it should load is vitals, is the object vitals. That's because when you save it to disk, it remembers what its original name was. And when you reload it later, it's going to recreate this object vitals. So just as a demonstration, I could exit out of R right now and then reopen it and then load vitals.r data from the disk, and now I would have a table, vitals, right back in memory. So that's valuable. On the other hand, I would have to change all my font sizes again, so I'm not going to do that. All right. For the last bit of the the demonstration today, we're going to work with an Excel file. A lot of people kind of make the assumption that I've got this Excel table. Now I'm going to have to export it as a TSV or a CSV in order to read it in R. And you can do that, and generally speaking, that's absolutely fine. But sometimes we find that Excel files have information on multiple pages. Hopefully you were able to download from the network our table of inventory here. I've got the name, but I haven't searched for it here. Okay, that's 201902226 inventory. Okay, right here. There. So I should be able to open in Excel this. Okay, so I have created a small inventory. These are our price guides, right? So I have lot numbers associated with the products. I can buy some dried newt, or fairy dust, or a bamboo staff, or a deluxe hat. You know, maybe I want to be a wizard today, right? So, and I've got a price marked with each one. Over here at inventory, I can buy from the Mowbray warehouse, or from Bellville, or from Musenberg, or from, so all of these. And for each of these lot numbers, I have a certain quantity associated with it to track current inventory. All right, so I want both of those, but I don't want to have to export each page as an independent document. So I'm now going to make use of install packages to make sure that I have the read.xl library in place. Now, if you don't have network access, this isn't going to work right now. But if you've already gone through installing it, you don't have to have network access anymore. So I have previously run install packages to install in the private library on this computer, the read.xl library. So really all I have to do at this point is to run the library command so that I gain access to all of the functions that are defined within read.xl. So just that quickly, that has made all of those commands accessible to me. If you got an error message at this point, it probably means that the package hasn't been installed yet. So once you run install packages read.xl, that should become available to you. Now, is it possible to get information about read.xl in a hurry, right? I've got the package installed here. Ah, look at that. So having used !read.xl, the whole library, I'm able to get a rapid bit of information back about what's involved in it. So I can find the main web page for it over at Tidyverse, which is a really, really useful collection of libraries. Tidyverse is pretty amazing. Who wrote it and stuff like that. I note that it's got a maintainer, and if I'm really, really stuck, like I just can't figure out how to get this library installed, I could write that maintainer and probably get some help. But don't pester people who do good work, okay? So try to work it out on your own, and when it doesn't work, then consult somebody appropriately. Okay, great. So read.xl is now installed, and we want to read individual pages from that. Now we remember that we had two worksheets, right? Inventory and prices were both sheets within this Excel library. So I'm going to start by trying to read just the inventory page from our Excel sheet. Okay. That's interesting what happened there. All right, so summary, inventory. There we go. So it recognizes that the lot numbers were numeric, but look at that, it's trying to do math on them. Does it make any sense to compute a median or a mean for lot numbers? Not really. We can see the quantity numbers. It's more or less reasonable to say what's the average number of products that are in hand, and here it's read the warehouse as character strings. So that's kind of an odd point, right? When we read a table to disk and created a data frame, it defaulted to calling things factors. But look at inventory warehouse. We read this from the Excel table, and yet it doesn't notice that Mowbray appears multiple times. It doesn't notice that Bellville appears multiple times. I would have to say factor inventory warehouse to coerce it into recognizing, oh, there are different levels here. Now it sees that Bellville appears multiple times, Mowbray appears multiple times, Musenberg just the once, but it still encodes it correctly as a factor. So you can get some kind of squirrely behavior like that. If you read a table from a text file in R, it will generally assume that character strings are factors. If you read it from Excel using that function, you're quite likely to see just a bunch of characters and not recognize them when they're factors. That distinction may not seem important right now, but occasionally we do kinds of computation that behave very differently for factors than they do for character strings. Well, for example, I'm going to repeat that factor command, and this time I'm going to say plot it. See, it notes that Bellville appears more frequently than does Mowbray than does Musenberg. But what happens if I try to plot that variable just as it was? Okay, so this time, instead of plotting the factor of it, I'm going to plot it just as it was retrieved off of the Excel file. That's a little squirrely, isn't it? We've got nothing. There's no plot method that's designed to run on just a bunch of strings. And see, it gave us back this very intuitive error message to say, I don't know how to plot this. I might suggest to the authors of this that including a I don't know how to plot this error could be pretty good. Okay. Right, so there was one other thing that we did. We loaded the prices off of there, I think. Did we already pull that out? Oh, no, I only did the inventory sheet. Okay. Reading from the same Excel file, but specifying a different sheet, gives us a different variable back. So inventory had just that sheet. Prices gave us back this sheet. Now I'm going to mention one other really curious thing here, and it's that the data type that came back is not a data frame and it's not a matrix. Do you see what that is? When I say, show me the current value of inventory, it tells me this is a tibble. A tibble. Tibble is a special kind of data structure that's used by a lot of things in tidyverse. And to give a course in R without mentioning tidyverse is malpractice. Because I got to tell you, a lot of people who use R every day swear by tidyverse and would very rarely use any of the graphing built into base R or the read.table function. They would try to handle everything through tidyverse commands like this. So a tibble is a sign that you are making use of a library that is part of this tidyverse universe. In a lot of respects, R with tidyverse is like a different language than R. A lot of the same things apply, but a lot of things are quite different. So I'm going to at least mention that tidyverse exists. A lot of the very, very most useful libraries in existence for R support tidyverse, are part of tidyverse. And a lot of times the things you'd want to try really require that you have tidyverse. We're going to have another encounter with tidyverse later in the week as we look at basically the library for plotting graphics called ggplot2. But for now, I'm just going to mention that what format the data are in can matter quite a lot. Having a tibble enables you to use a lot of tidyverse functions that having a simple data frame won't. There are, however, lots of functions for adapting from one to the other. Okay, with that, I note that it is 12 o'clock and it is time for me to release you to lunch. But it's been really lovely working with you today, and I look forward to seeing you tomorrow morning at 9 o'clock.